today's session is just to try to basically complete the explanation about this chapter. We're going to say a couple of words about this. Is something which is very, very useful, right? Because in some cases you have to calculate the shear stress in a hull, in a ship hull, right? Especially for tankers. I had to do it in some occasions. And it's very, very important because the calculation is very complex, right? It's very useful to have a general step or general procedure to check your results. And you can do that if you compare the maximum stress with the mean stress. And we're going to say something about that in the two examples that we have completed. Then I just posted this morning a couple of figures with ship sections and the distribution of shear stress. So we can look it up, okay, and see the characteristics that we have seen in our beams. Our beams are very simple, but still you will see a lot of similarities with the case of the ship. Then I'm going to explain that this very short explanation on, as a result of considering the shear in the section, okay, we will have to accept that the section, which is started straight, rotates, but also it suffers some distortion, axial distortion. And you said immediately, hold it, just a minute. We started saying that kinematic assumption is taken, it's assumed as valid. Yes, it is, but we have to accept that it is valid, but we still have to accept that we need to break it just a little bit. Okay, more or less, that's the idea. So that's why some people do not like the formulation that we are using. It's useful. Okay, and at the end, hopefully the last minutes of this session, I will give some minutes in order to answer questions about the assignment. Okay, so that's the agenda for today. So let's start by, okay, let me go back to the exam here. Andy Miranda, can you see my full screen? Full screen? Okay, so here we have the distribution, right? Okay, we started, and here, in this part, the distribution is linear. That's what we're seeing here. We have a jump because if we make a cut just below the top of the web, here, you have to consider not only this, but also the other side, right? And now, in the vertical element, we have a quadratic distribution with a maximum value here of 745. Yeah, 745. So that's this value here, 745. Okay, now it's very useful to calculate the mean value of the stress. Okay, so we can compare the maximum with the mean. The mean is presented here with this non-continuous line. Okay, to calculate the mean, since we know that the horizontal elements do not contribute to recuperate the V, the shear force, we only consider the vertical elements, okay? So, I don't like red. I don't like red here. So, to check our calculations, we can calculate Sorry about this interruption. Let me please. Can you see my full screen?
Yes.
Andy?
Yes.
Okay. I'm sorry about this interruption. So the height is 30 and the thickness, I think, is 125, right? Centimeters. Yeah, 125. So we can calculate now here, we can calculate the mean stress. So the shear force, it's 25,000, this is kilograms, and the area is going to be 30 times 1.25, this is square centimeters. Okay, so that's that. So I have a value of 667 kilograms per square centimeters. And you see that the maximum is a little bit above the mean, because in here you see that the mean is above the shear stress. And all of this, remember, you have to recuperate the shear force. So here you are below, here you are above. So as an average, it goes like this. Okay, so you can calculate the maximum shear stress, and to check, what you can do is you can calculate the mean. But to calculate the mean, you have to consider only the vertical elements. Okay, in this case, is just the web. Okay, let's do this in the second example that we just started. So this is the example that we are considering. Okay, and in this case, we have two webs. Okay, not only one, but two webs. And also, we are going to calculate the maximum shear stress. Okay, so I have here. Okay, here, let me go one more on. But let's do it here. Okay, let's calculate the maximum shear stress. I can find here. So let's calculate tau max. Okay, so to calculate the max, we have to consider the elements which are above the neutral axis. Above neutral axis. So in here, the neutral axis goes up like this. So we have this element, A, half of the board B, and the board C. Okay, so the most important part here is okay, so we're going to divide it Q at A, Q of B, and Q of C. Okay, everybody calculate it, and then I will ask somebody to participate. You calculate the Q of A, B, and C, considering that right now I'm doing a cut at position Y equals 0. That's on the neutral axis. So everybody, please calculate Q at A, B, of A, B, and C regions. And I will ask somebody to participate. Please don't take too much, because our agenda is long today, okay? Okay, let's go on. Mr. Chin Chin, did you have Q of A Mr. Chinchin?
Q of A is equal to 10 multiplied by 2 and multiplied by 7.
7. Okay, so we have, yeah, 10 is the width, is the width, I'm sorry, 2 is the height, and 7 is the distance from so is that 7?
No, it's 6, doctor.
6.
Sorry.
6. Yes, no problem, 6. So that gives us how much? That's 12. That is cubic inches, right? Q of B. Thank you. Miss Puertas, give me Q of B. Q of B. Remember, let me cross here. See, we have already considered this part. Okay, so Q of B, let me change color. Q of B, it's only this. Okay, Miss Puertas, please, Q of B, how much is that? Miss Puertas, are you there? Come on, don't make me waste time.
Yes, I am here, teacher.
Okay. So the area, Miss Puertas, how much is the area?
5, 2, and 10.
5, 2, yes, 5 times 2. And the height?
5, 2.
And the height?
And 12.
No.
No.
No. If the height is 5, just
8,
to the
8.
No.
4.
Remember here, I'm crossing the you see, do you see my area here in green?
Yes, teacher, sorry, I confused. It's 4.
No problem. So this is the centroid. So you need to give me the distance from here to here. So if this from here to here is 5, so this is half. So it's going to be 2.5, I think, right? Correct me if I'm wrong, somebody. So here is 5 divided by 2. So sometimes it's easy to remember this. Okay, this is the thickness divided by 2, and this is half h squared minus y squared. In this case, half h is 10 because you are considering only the web. So you have 14 total, and you take 2 inches in the top, 2 inches in the bottom, so you have 10. So 10 divided by 2, that's 5 squared. And that's what you have here. Okay? So it's going to be what? 25, right? So this is 25, and this is inches cubed. And finally, let's go to the element C. Let's see, Mr. Sawai, are you there, Mr. Sawai? Mr. Sawai, are you there? Mr. Sawai, please don't make me waste time. Mr. Sawai, Q of C. No?
She wrote in the chat, so just yes.
Who is speaking?
And the doctor.
Okay, what happened?
Sawai just wrote in the chat.
Okay, what did he write?
But not say the answers.
Okay.
Doctor.
Let me go on. Mr. Pesantes, are you there, Mr. Pesantes? Give me the Q of C. Mr. Pesantes, are you there? Come on.
Yes, doctor.
Tell me. The area. How much is the area?
Is 2 plus 2 plus
No, 2 times multiply.
Okay. 6.
Okay, that 2 divided by 6, that's the area. And then we need an H. So from here to here.
2.
2, yes, okay. So that's 2, 4, 24.
24, yeah.
So we can add these three things. And we can have that Q max. It's going to be 120, 145, 149 inches cubed.
Doctor, I have a question.
Yes.
I'm
Somebody has-
Janos, doctor. In the QA,
In
why
the
is
what?
in the QA? Why is the is 6? For me, is 5.
No. The area in yellow, okay, the total width is 10, but you have 2 on the left and 2 on the right from the webs.
No,
So
Q.
track that, people get
The first Q, doctor. The first Q.
pardon me?
The first QA.
QA.
Yes, doctor.
Okay, so I have this area.
Yes.
So the total area, the total width is 10.
Yes.
And the height of this board is 2. And then the distance from here to half of this, only up to here.
Well, it's not the centroid of the.
Yeah, but this is here. From
For me,
here,
it's 5.
I have 1, 3, 5, and 6.
6.
The centroid is here.
Yes.
And this is the neutral axis of the whole section. So you have 1, 3, 5, 6.
Okay. Okay.
Doctor, the Q max, the Q total, or Q max.
We're going to calculate the Q max because we're interested in the tau max. Okay.
No, I can see the Q max is 169.
69, is it?
Yeah.
Oh yeah, you're right. Thank you. My arithmetic is in trouble. Thank you very much.
Okay.
Doctor, one question. The element of the right side don't consider?
Oh yeah, you're right. So this has to be multiplied by 2. And thank you very much. So so it's 15, 170, and 194, right? There. Okay, so we have everything. Tau max. Mr. Carriel, what's the formulation to calculate the tau? Mr. Carriel? Mr. Carriel, are you there? Oh man. Mr. Medina, what's the formulation to calculate tau? Jesus Christ.
One moment, please, teacher.
No. You should, I mean, right now, if you are working in this class, you should have this formulation in your memory. Mr. Ortega, Mr. Ortega, are you there?
Yes,
do you
doctor.
remember the formulation for this, for tau?
Yes, shear force.
Shear force, V, okay?
Multiply Q.
By Q max, in this case, is the max, and divided by
Inertia
I sub C, and
by V large.
exactly, that's the width. So let me go, okay, I'm going to put it here. The shear force, anybody remembers the value of the shear force? Let me go back.
1900.
1900, okay, that's 1900, we put it in here. I don't have a space, so we know that it's going to be pounds and inches, okay? The Q max is 194, and we divide it by the inertia. We gave the inertia, right?
1900.
1900, so it's the same. And B, we have to be careful, right? Because right now, the cut considers both sides. Okay, so it's going to be 4. Let's put it 2 by 2. Please, calculators.
$48.5.
So this is 48, how much? 48 point?
5.
So this is PSI. So this value here in the distribution, okay, this value here, it's 48.5. And now, to check our results, on the left, I'm going to calculate the average. Okay, so the shear force is 1900. Okay, this is pounds. And the area, Ms. Jurado, tell me, what's the area of the vertical elements here? Ms. Jurado, please. No. Mr. Iturralde, the total area of the vertical elements. No. Mr. Hidrobo.
Present. 40 inches square.
No. Okay. 14 is
20 and 10.
It's kind of difficult, right? Yeah, we have to be careful, right? Because it's the whole, see, it's the whole height by 2. But then we have to consider both sides. So it's going to be twice because we have 2 webs. And then we go, the height is 14 and the width of each one is 2. Okay. Can you help me with this?
Doctor, why is 14?
Total height of the total height. You have, I don't want to draw here because we already have a complex. See, we go, all of this develops shear stress. These corners are a little bit controversial, right? Because we have some horizontal and some vertical.
Yeah, is 12.
How much?
I believe it's 12. Two in the
So it's
in the
2,
length. Yeah.
it's
1,
2,
2, 3.
4, 6, 8, 10, 12. Oh yeah, you're right.
Okay.
Oh, it's 14. So I have this, then I have a space. I have this and a space, this and a space, and this. So I have 3 boards and 2 spaces.
1, 2, 3, 4, 5, 6, 7.
That's correct. It's 14, including the corners. It's 14.
So it's
Okay.
we have 4 boards and 2 and 3 spaces. Yeah, this is 14.
Yeah. Sorry.
No problem. We are here to discuss. Yeah, it's 14. Please, could you please give me the results?
33 and 92
pounds.
33.93.
So it's about 34.
Yes.
Okay, so this is 48 and the average is about this. more or less. Okay, so that's the average. Okay, so it's always a good idea that you check the value, the maximum compared with the mean. Okay, so of course the maximum has to be larger than the mean, but the difference is usually not that much. Okay, maybe, for example, in the previous case, I think it was about 12% of difference. Here, the section is a little bit more complex. And also, there is this doubt about the corners. And we include it completely. And I don't think that's quite correct. But anyway, so it's a good idea for you to check, okay? So if you have to calculate this, it's always a good idea to calculate the average. Yes, please.
I have a question. I am a little confused when you calculate the maximum shear stress. Why the denominator is 2 times 2? Just in that. I think that was only 2.
2 times what? Which one? Which part? A, B, or C?
When we want to calculate the maximum shear stress in the formula.
Okay, yeah.
Okay. The inertia, the B.
Oh, okay. This yeah. No, the problem is this. Right now, this is what we are doing. We are considering this is what we are doing. Okay, I'm taking the upper half, right? This is the section. So I have this is the imbalance force. And in this cut and in this cut, we are going to have some tau. So we have to consider both areas, this one here and also this one here, in order to equilibrate the whole section. That's what we need, both cuts, the area of both cuts to be included in the calculation.
And in this case, because both are the same, we consider 2 and 2.
Yes. What some authors prefer is this, okay? Instead of calculating the whole section, what you can do is you can calculate only half. Okay? In this case, you have this DFS, but in this case, in here, there is no shear. Because remember, this is a symmetric section. You only have this one here. In this case, you have to consider only half of the Q. So everything will divide it by 2. So it's the same.
Excuse me, doctor. I got a question. That problem is depend of exercise, right? Because B maybe can be for the one section. B only have one value, and maybe for section A, so B will be 2. No.
See, what you have to do is, that's why I suggested last session. When you do these things, try to draw a clear sketch, a clear figure. And what I just did here, I'm showing you 2. Maybe if you want, what we can do is, let's see, we can draw in a new page, okay? Because we are very, let me open a new.
Doctor, I have another question about that example.
No problem. Let me open again. Okay, we are here. Then we switch. Okay. My suggestion always is draw something very clear. Okay. And this is what I need you to do. Okay. Let's draw I don't like that color. Okay. What I say is this. Okay, I have the whole section. This is the neutral axis. Okay, and you have dfs, and this is equal to v, q, and inertia times dx. Okay, now if you see this, this is the net force on the whole sector. So we need this stress and this stress to have this in equilibrium. Now, let's call it Q1. Now, down here, see, this is the full section. This is exactly this one. Now, I'm only going to consider this part. Okay, I have DFS, and DFS is going to be V Q2 dx divided by the inertia. Now, in this cut, there is no shear stress because it's a symmetric section. And that's what we explain in here. So here I have no shear stress. And here I have a value of tau. So let's call this tau 1. And this is, we call it tau 2. What's the relationship between Q1 and Q2? See, this is Q1 and this is Q2. What's the relationship between this and that? I don't know who was asking this. What's the relationship between Q1 and Q2? Anybody?
We have the same word.
Pardon me? Come again, please. How much is this Q1? And that's what's the relationship between and with respect to Q2?
Q2 should be the half of the Q1.
Exactly, exactly. So this DF is going to be half of that. Now, the area where this stress is acting, okay, this is only on one side. This is twice, but you have this and you have that. So as a result, you're going to have the same stress because it's a symmetric section. Okay, so yeah, you need to consider this area and also this area. Okay, and this area is going to be the thickness times dx, the thickness times dx. That's why when we consider both sides, we need to consider both cuts. This is what we have here. I don't know if I answered the question that some of you were asking. Somebody was asking me about this number 2 here. Yeah, and we need to consider both sides. That's why we include this 2 here. And that's why here we multiply this by 2. And in here, we consider the whole deck. Okay, and here we consider the whole width of the yellow of Q of C. So that means that we're doing cut here and also cut here. And because of symmetry, we have considered that both shear stresses were the same. Okay? Any other question, people? About this? So the next point in this morning is the distribution of the shear stress in a real ship section. Okay, I can, or you can look it up in the literature. There are many of these diagrams. Okay, so here I have this. This is the deck of the ship. Here I have a hull. Okay, So it's like a hatch. So you can put loads inside the hull. So this is the side of the ship, side. This is the bottom. And this is the inner bottom or double bottom, whatever you want to call it. Okay? So this is the neutral axis. Okay. And you see that this is on the left, this is the normal stress. And the deck, since the distance is very large, you can expect a large value of the normal stress. How do you evaluate the normal stress, Ms. Valdez? How do you evaluate this value here? How do you evaluate that? How do you calculate
The
this?
bending moment.
But tell me the formula.
Bending moment
Times
inertia.
no, divided by inertia. Oh, come on.
The distance
Right.
over inertia.
Okay, so yes, the larger the distance, the higher the stress. Okay, so that's why you can expect this value to be very large. Now, on the bottom, you see that these arrows are pointing upward, and these arrows are pointing downward. That means that the sign is different. Yes, on the top, y is positive. On the bottom, y is negative. Now, here on the right of this figure is what I want you to look. We have the same section, but now this is tau. Okay, so here it's open. So the stress here would be 0. And from that point, you start calculating the shear and increases linearly. Okay, so if this thickness is the same as this one, then this value is going to be equal to that one. That's why we usually do this like this. Now, in the side, remember, we have a y squared, right? So the distribution is quadratic. And you can see immediately this is not linear, this is quadratic. And here, you have the max. And you start decreasing here until this point here. Now here, we have a bifurcation. So some of the shear flow goes in that direction, and the rest goes in this direction. Okay, so if we make a cut here, let's call this cut A. Okay, we have to consider the side and the deck. And with this Q, we calculate this value of shear stress. Okay, now, if we make a cut down here, cut B, then you have to consider the same as before, but now you have to include all of this area. Since you are below the neutral axis, the Q will be smaller. And that's why you see it here. You have a jump. So at B. And then you can go on following this quadratic. If the thickness on the side and at the bottom here are the same, then you can do this. And this value here is going to be the same as this one here. And then you go again, linearly decreasing until here. On the inner bottom, see, this is the inner bottom. See, some of this went in this direction. Remember that what you can do is you can make a cut here and integrate from here to here instead of considering the whole section. We did this exercise in class for those of you who come to class, okay? But you have to be careful with the sign. And then this has a linear variation because the distance to the centroid of the sector is constant. So there is only variation in area. And you see that it's decreasing decreasing until the center line, which is in here. Okay, so that's the variation of a shear stress. That's the variation of a normal stress. Questions about this, people? Questions? Any questions about this? No questions. Good. In here, we have something similar. Okay, this could be a large cargo vessel, right? You see that you have two decks, and both decks have openings. Okay, so again, we start here, which is open. We can neglect this reinforcement, and we can go and increase linearly on the deck. In this case, you see that you are not considering tau, you are considering the shear flow. How do you calculate the shear stress from the shear flow? Miss Arechua, how do you calculate the shear stress from the shear flow? Miss Arechua. Are you there? Are you there?
Yes,
no?
doctor.
Okay. Do you remember how to calculate tau from Q, little q?
From little Q over V.
Exactly. So at any point that you want to calculate the shear stress, what you do is you make a cut where you want to see, calculate the value, get the little q and divide it by the thickness at that point. And that's it.
Doctor, I have a question.
Yeah, go on.
In this case, is only one B?
One what?
One B. For calculating the shear
Yes.
stress.
Yeah, we're only considering one side. Yes.
Oh, it's not with the about the case of
the problem here.
Yes.
No, you have to be careful. That's why the problem here is the large Q. Okay. Okay, here. If you make a cut and consider up to here, this is the case. And in this case, Q is going to consider the whole section. In here, I'm drawing only half of that. So in this case, you're seeing clearly that you are only including half. So there should be no doubt. Okay?
Okay.
No problem, no problem. So linear, quadratic, and here I have a bifurcation. So we have 0 here and increases linearly onto here. So in this point, okay, again, if you make a cut in here, this is what you obtain. If you make a cut just a little bit below the bifurcation, then you have to consider this area and also the area from the lower deck. That's why you have an increment from here to here. Then you can continue. You find the maximum at the neutral axis. Start decreasing because you are adding area below the neutral axis. So the distance from this contribution, okay, the distance to the centroid of this contribution is negative. So you start decreasing, and then you see it here decreasing. Here again, you bifurcate. Some of the flow goes in this direction and the rest goes in that direction. Now here we have a problem. Because here, some of the flow goes down and some of the flow goes up. Okay, so you have something like this. But you know that the first moment is continuous. So what you can expect is that as you make cuts in this vertical element, right, you're going to find a point where the Q is 0. What is that? I don't know. So every time you have a longitudinal bulkhead, we have to be careful. Usually, what happens is that we cannot solve right now in chapter 2 this type of problem. We will solve that using another relation which will be explained at the end of the semester. Okay? We have this jump in the bottom here, and then we go straight to the center line. Okay, you can see the relations of this. Let me go to this case. Okay, it's like having one intermediate deck, and this is the jump that you have. Okay, in this case, the flow is pointing downward. Okay, so you take this shear flow, transform it into shear stress, and integrate vertically from here up to here. And the result of that should be what? If you integrate in this part, the shear stress, what are you going to obtain? What are you going to obtain?
The area under that curve.
No, not the area. What are you going to obtain if you integrate the shear stress on this part of the section? What are you going to obtain?
Shear force.
Exactly, exactly. Because remember that the vertical elements will have to reproduce the shear force. Okay, if you integrate the force here, the shear stress here, you are going to obtain a force to the left, to the right. But on the other side of the ship, there's going to be another force pointing to the left, and the two will cancel. Similarly with the other deck, similarly with the bottom, similarly with the double bottom. Okay? Why? Because we have only forces acting in the vertical direction. Okay, people, is there any questions about this? Any questions about this? No? Okay. How about the assignment? Have you started the assignment? Anybody? Would you please do me a favor? I just want to see in general how you people are doing. Would you please raise your hand who have done one of the problems of the assignment? I have 3 problems. Any of you have done one of the assignments of the problems of the assignment? Any of you? Raise your hand. Oh, nobody. Jesus Christ, I'm in trouble here. Oh, no. Here we have some. Good, good. Who have not started the homework yet? Please, everybody, lower your hand. Lower your hands. Has not started the homework at all. At all. I mean, you have not downloaded the problem formulations. No, that means that everybody has already started. Good. Okay. Well, remember, this is due next Thursday. At Thursday at 8 a.m., we are going to have the evaluation. It's going to be closed book. Closed book. Okay. And what we are going to be doing is I'm going to organize the order of the presentations. Okay, so some of you will have to come on Wednesday for the lab, and some will come Friday morning for the lab. What we're going to do is on Tuesday, I'm going to explain what you are supposed to be doing in the lab. Okay, so everybody will understand what you're supposed to do. Then on Wednesday, okay, some of you will come, okay? Some will go to the lab and the other will stay with me in the auditorium. And what I'm going to do is I'm going to give you a couple of minutes to explain me something about either homework 1 or homework 2. I'm going to give you a marker and you have to explain it to me. Okay, So when people in the lab complete the experiment, they will come to the auditorium and one of the groups will go to the lab. And at the end, everybody will do the lab and also the presentation. It's open, so everybody can be listening to the presentation from the other students. There will be no PowerPoint, it's just chalk, a marker and a blackboard. That's all what you have, okay? So you can practice your English during this presentation. And yeah, I know it's gonna be a little bit nervous, but we have to handle that. Any questions about this, about our plan? Any questions? If the person from outside the city have problems coming on Wednesday or Friday, let us know. So we can, if you have problems coming on Wednesday, we will move you to Friday. Okay, and the other way too. But we need to know. Otherwise, we will go on and we will organize the presentations randomly for Wednesday and Friday. So I see you Wednesday, Thursday for the evaluation, and Friday again for the lab. If some people want to do some sport, yes, Friday afternoon, I'm ready for you. I'm practicing. Okay, questions? Any questions?
Yes, doctor.
Go on.
Good morning, doctor. I have a question about the zero exercise of the homework.
Okay.
Yes, and my problem is that I don't know what I need to do. So
okay, no problem. Okay, I
yes.
Okay, see, the thing is this in general. Okay, the other day we had a meeting with some of the industry representatives, and they told us that one of the characteristics of the skills that graduates from our are not that prepared in the experience of using regulations in general. So there are some regulations that you need to familiarize, and that's what we want from you. So you can open the regulations, the rules from the Society of Classification Rules, Classification Society. Okay, so you have to open, and well, not open physically, right? You have to go into the web and in the Det Norske Veritas, okay? And I'm leading you because that's a very large, it's a large platform. So I'm leading you. See, of course, this is a maritime area. Of course, you are interested in the ship regulations. And in there, look for the rules for classification general. Because there are specific rules, for example, for certain type of ships. So we want you to take a quick look at the general regulations. And in there, look for the part 3, chapter 5, which deals with hull girder strength. And in there, what we want from you is get the value that you can use for allowable shear stress. So we know that if we have a piece, remember, I guess, I don't know if you did the test in the lab. You take a specimen and you pull it, right? And you can calculate from those results, Young modulus, Poisson ratio, Gilles point, ultimate stress. But in this case, you are pulling. So this is normal stress, right? And the value is there, it's 235. That's the key value that you have to remember from now on. But that's for normal stress. The value that we're interested right now is the value for shear stress. It's not the same, it's lower than that. So that's what we need from you. So you get familiarized with these rules, have a general idea how many chapters, okay, more or less what's in chapter 5, what do you have in there? take a quick look so you can start familiarizing with that. But specifically, the information, Ms. Avilés, the information that we need from you is get the value of the allowable shear stress for the common steel. That's the information that we need. And try to put it in your memory. So 235 for normal stress. How much is for shear? That's what you have to look for in the Norske Veritas rules. Ms. Avilés?
Yes, doctor. Thank you.
No problem. No problem. Anybody else?
Doctor, I have another question.
Yeah, go on. Go on. No problem.
Yes, and it's about the Excel course online. I did a course, but I don't know how can I to prove that I did the course, because when I end in the course and I see on the
at any point of the course of the you took the module, at any point, try to get some capture of the screen so we can see that you have really do it.
Yes, doctor, but in my case, I did the course in the first day of the class, so I don't have a capture about this. So I need to repeat the course.
Remember, why don't you get into the system again this weekend and try to do a little piece of that and capture that, and you present that as a proof.
Okay. Okay, doctor.
Okay. Any other questions, people?
And after we do the capture, how we send an email to you or
No, not to me now. No, I had too many emails. Andy, Miranda, you're going to receive that, or Maria Daniela? Who is going to receive that? To you?
Yeah.
Okay, so everybody has to send that to Andy Miranda. Okay. Any other question, people? Any other question? No?
Yes, doctor, I got another question.
Yeah, go on.
The presentation with you has a score?
No. 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 All I want from you is that you, the problem is this, I have to be completely honest. Completely honest. It's very difficult for me to grade an English presentation if I have to grade only the presentation. The technical side, I don't have problems because I like structures. But right now, we're trying to make you practice English presentation. So don't worry about that. I mean, if you did your homework, you shouldn't have any problem explaining something. If you copy the homework, then I will see you in there. That's the summary of the whole thing. Okay? If you did your homework, there should be no problem. If you copy the homework, then we'll see what happens. I'm not going to grade it. I just want you to practice your English and practice your English in an engineering situation. Okay, people, I'm tired. And I'll see you Tuesday. If you have problems, you know Andy, you know Maria Daniela, you know Engineer Isaac,